Recording. Good morning. From Monday, I guess it was, just a little bit of review, not therefore, but what we spent a lot of time doing and working on was moving from this standard form. So this is called standard form. Of a quadratic, ax squared plus bx plus c, and moving to transformation form, which has its benefits, the main one being that it gives us the vertex, right? And so this is transformation form. Now, in transformation form, the vertex is when x equals h. And so we found that the vertex is at, is at hk. What was another way that we could find k? We could say, okay, well, if I have some quadratic, then I know in general the shape is going to look like this, right? Like x squared, a little bit of activity, bless you. Then here, this is going to be when x is h and when y is k, but what can you do instead? You could say, well, that's the same thing as f of h, right? Whatever the function is, the quadratic is, evaluated at h, right? Because that's your input, k is your output. And so sometimes it's easier to just find f of h instead of this k, right? And so what we did was we said, okay, if I can transform this ax squared plus bx plus c into a times x minus h squared plus k, then it's easy to find the vertex. Why do we care about the vertex? We care about the vertex because it's either going to be a maximum or a minimum in this case, right? So a minimum value, right? Or the alternative is if it's upside down, then your vertex is still at hk, and then it would be your maximum, depending on which way it's facing. So that's useful because often we want to optimize something, which is either maximize or minimize, whatever floats our boat, right? And so h, if I have to find h, which is the key to all this, right? That's the x value that maximizes or minimizes this thing. Then I take, my iPad's a little possessed today. Should have restarted it, I think. We take the b from the standard form and then divide it by -2a, or sometimes I'll put the negative up top here. Negative can float around, but -b over 2a, so the a comes from here. And that's just going to be a value, right? And then I can evaluate the function at that value to find k. Or you can use this version, whatever you prefer. All right, let's see here. I did not set myself up very well, did I? Did we do anything else? No, we kind of focused on that. We did a problem, right? That fencing problem, and we maximized the area, I think it was. Oops. Oh, it's being so slow. We found, we made a quadratic for finding the area of that fenced in pen, I guess, or garden or whatever it was. right? And it's a function of the length of one of the short sides of the rectangle, or potentially short sides, right? And then what we did was we said, okay, what value of L maximizes the area? Well, if we plot this, right, it would look something like this, and then we're looking for the vertex. Right? And then we were able to just grab A, B, and C and find the output when it's maximized was 800 square feet. And that's where we ended off. Okay. Don't you just hate it when things are slow? I'm supposed to be the slow one in this iPad me relationship. This one, I want to do this one. Okay. How about for those other two examples, I'll add them into the notes so you can see them, but they're very similar to what we've seen already. This one's a little bit weird, so I want to do this one. So we've got this Norman window. Okay. Let's see if I can pull this off on the fly. Ah. Okay. So a Norman window has the shape of a rectangle surmounted by a semicircle. So it looks like this. So it's got a rectangle here, and then it's got this semicircle, but it's kind of a bad semicircle. Still bad, but whatever. Arguably worse. Fine. I can't hack it. There. Ah, beautiful. Okay. So we've got this Norman window, and the reason that I want to do one of these is because now we've got a circle, which usually involves some sort of pi, right? Regardless of if we're talking about the circumference of the circle, right? The distance around the circle, or the area of a circle, it will involve pi. So it's a little bit more, little bit sneaky, right? But let's go ahead. And so if you want a Norman window with perimeter 40 feet, what dimensions will maximize the area? Okay. Can I pull this off first thing in the morning? I don't know. Time will tell. Let's see here. So what do we want? And when do we want it? We want this to be 40 feet. It's not very helpful, right? But we can break it up into little pieces. We want to maximize the area. Okay. The area of a rectangle is fine, but let's remember the area of a circle. Pi r squared. I almost said 2 pi r. Pi r squared, where r is the radius. Right. How about the circumference of a circle? Because we also want that, right? We want this driving me nuts. We want this distance to be part of the 40 feet, right? And so the circumference of a circle will need that as well, is 2 pi r. Okay. What can we do? All right. We can, well, we can start here with the radius, right? So this distance here has to be 2r, right? regardless of what the radius is, we're allowing it to fluctuate. And so this distance has to be 2r. Okay, that's good, which means that this distance is 2r. Okay, now for any r, what's this distance? This has to be 2 pi r divided by 2, right? Just a half. Nice. So here, this distance has to be 2 pi r divided by 2, which is just pi r. Okay, pretty good so far. We've got the end caps, right? And so now, what do we want? We want the total to be 40, but we know that it's not going to be a lopsided window. That'd be weird, right? And it's a rectangle. We were told that. And so this distance and this distance are going to be, they're going to be the same, right? And so for now, I'm just going to use x as a placeholder, x and x, because then I'll be able to write this out. And let's see here. So the perimeter has to be, starting with this side, maybe, because I drew my little loop this way, has to be x plus pi r plus x plus 2r. But we're also forcing that to be 40, right? That was our constraint. So that means that 40 is equal to, I'm going to say 2x plus pi r plus 2r. I could combine the 2 pi times r, but I'm just going to leave it for now. And then if it simplifies things later, maybe I will. Okay. But what do I want to do? I've got this x in here and this r in here, and that's a problem because I really only want to have one variable, and ideally I want it to be r, right? And so what am I going to do? I'm going to solve for x in terms of r. Let's see here. So I get 40 minus pi r minus 2r, and then divided by 2. So let's see here. I get, can I jump this far? I'll do one step in between. 2x is 40 minus pi r minus 2r, which means that x, I'll put it on the new page, is 40 minus pi r minus 2r divided by 2. And like I said, if you prefer to collect like terms, because pi is just a number and 2 is just a number, so I can pull out that common r if you want to. Sure. I'll do it in light blue because it's kind of optional here. 40 minus r times pi, I'll do plus 2 because I pulled out a common negative r, and then divide by 2. Okay, so now we have x as a function of r. That's good. So here, now x is a function of r. Okay. So we could replace this x with something in terms of r. So let's do that. Go back up here. X is, it's going to be kind of nasty. 40 minus r times pi plus 2 divided by 2. Same thing over here. Write it super weird, like this. They're the same, right? What was our goal? Uh-oh. We want to find what dimensions will maximize the area. So we need a function for the area, which we can find. So we need a function for the area. I'm going to break it up into two parts. Right, I've got the rectangle, which I can find the area of. This was 2r, and this was 40 minus r times pi plus 2 divided by 2. A little bit nasty. If you want to use x still, you can, and then substitute it later. And then this had the area of a circle is pi r squared. So this area must be pi r squared divided by 2. And this area must be 2r times 40 minus r times pi plus 2 divided by 2. All right, that's good. So now we can add those areas together. So it is pretty nasty looking, especially with this side, right? But if you just think of it as, okay, you've got this length of one side, you can use x for a little while longer if you want, but it's nice to only have one variable, right? One r, I guess. So then the total area as a function of r, step it up a little bit, because r is the variable in here, is going to be 2r times 40 minus r times pi plus 2 divided by 2 plus pi r squared divided by 2. Can't decide if I should cancel this 2 or should I use this 2 to combine like terms? It's not obvious to me which one's gonna make things better. We have a preference. I can't do both, right? Because there's no 2 to cancel with here, right? So that's too bad, right? Maybe I'll just leave it like this for a little bit. Or okay. I've made a decision. Might be a poor one. Because I want to expand this out and make it look like a proper quadratic, right? That's what we're working with. And so let's see here. All right, here we go. R times, I'm going to expand this in here. So I get 40r minus r squared times pi plus 2 plus pi r squared over 2. I've got a common multiple of r squared that I can collect. And how am I going to do that? I'm going to pull it out front. R squared. Oof. How rude is this? Pi over 2 minus pi plus 2. So many switcheroos. What did I do? I pulled out the r squared. I'll do a little map here. I pulled out the common r squared. And then I took this negative, lumped it with this, and I tacked it on at the end. Because a negative plus a positive is the same thing as the positive plus a negative. And that one is positive.
What
So
happened to the 40 now?
Still TBD.
Ah.
There.
That'd be nice. Yeah.
This is just a number though. It's not very nice, right? But it is just a number. Pi over 2 is a number, minus pi plus 2 is a number, right? So it's just a coefficient. It's just a very ugly coefficient, right? Not as nice as the 40 here. There's a lot of math profs that talk about hand wavy math. And then some things happened, and then obviously this happened. Felt very hand wavy. I just did some stuff, and then ta-da. But there was, yeah, I could have done it in, I guess, 4 more lines, right? Doing one thing at a time.
No, that's okay.
You don't wanna? I think we're okay. There. Okay, so in terms of a quadratic, right, this is really plus 0, right? Now we have it in the form, in standard form, ax squared plus bx plus c. So here we've got ax squared plus bx plus c. This is my a, right? Kind of big and gross. And this is my b, the 40 is my b, and c in this case is 0. Okay, good. What were we trying to do here? We wanted to maximize the area, I want to say. Has to be a maximum. Why? Because the coefficient a is positive, right? And so it's going to be facing up, so no. Is it negative? Why does it has to be negative? But I was thrown by this. Pi over 2 is less than pi, so it's going to be negative. A is negative. There. All right. And you can do it on your calculator. Let's see here. You found your pi button on here? It's kind of sneaky. It's down by the answer button, the previous answer button. And so you have to go shift and then pi, but it does have the pi, and it gives you the answer in a nice exact format. So if I'm going to go pi divided by 2, and then minus bracket pi plus 2, exactly as it appears. Hey, it didn't give it to me in exact form. I just said it would. Didn't want to. A is negative. A is roughly negative 3.571. Go to 3 decimal places. Sounds good. Should we rewrite this with the approximation? Why not? I'm okay with that. This is negative 3.571 r squared plus 40r, and I'll drop the plus 0 because it doesn't do anything. So now it makes sense that we want to maximize the area, right? This is the maximum. Has to be pointing down for us to be able to maximize it, right? And it has to be pointing up in order for us to minimize it. So that's why I had the little moment where I thought, no, it has to be negative because it has to be facing down, right? And so let's see here. This happens at HK, which we can find by, so if we need to find the vertex, is at H negative B over 2A, pretty sure. Negative B, which is negative 40 divided by 2 times. Now, if you wanted to, you could keep all the pi's and do all that fun stuff, but putting it over a common denominator of 2 is going to make it a little bit easier. Why? Because then it's going to cancel with this 2. I feel like I should do it. Keeping the fine. You don't have to ask me twice. Well, maybe you do. Or pi minus 2 pi plus 2 divided by 2, which is approximately negative 3.571. I multiplied both sides by, or this side, the pi plus 2 times 2 times 2. Man, words, but why?
Yeah.
Because in order to add or subtract fractions, right, I need to have a common denominator. And so I use my sneaky trick of multiplying by 1 because that doesn't change anything. And so if I need a common denominator of 2, then if I multiply by 2 over 2, it doesn't change pi plus 2. I'm just multiplying by 1. But now I have this 2 here. So that's where that came from. And I have this common denominator of 2. And that's when I can put it all over 2. Right? We use that trick a lot. Where we multiply by 1, but sometimes that 1 can be quite elaborate, right? You could have a very large number over itself and it's still just 1, right? And so now, if I put this, let's do the approximation first. A is negative 3.571. Approximation, and I'll do the exact version. Oops. The exact version. Exact is just when I keep the pi as pi, right? Keep all the fractions. Then I get h is negative 40 still divided by 2 times pi minus 2 pi plus 2, all divided by 2. When I saw this 2, that's when I realized I could go back and kind of make this a little bit simpler and say, okay, then those would just cancel, right? 2 divided by 2 makes 1, so I can cancel those out. And so now I'm left with an h of negative 40 divided by pi minus 2 times pi plus 2, which I can simplify a little bit better. Negative 40 divided by pi minus 2 pi, which is negative pi minus 4, negative pi minus 4. Let's see here. Going back to the approximation, on my calculator, if I do, now I've got all the numbers on my screen, and usually I would just keep that and multiply it by 2 and then do negative 40 divided by that. And that's where this previous answer button comes in handy, right? And so whatever the previous answer was, you can do negative 40 divided by that previous answer. And so that's really handy. There's a store button as well where you can, if you have really long numbers, you can store them. Have you worked?
Which function, what buttons do you have to push for that?
Here, let me grab, where's that, my beautiful picture of my calculator here. Because it's really, really handy. So I want you to see it. Let me crop this up. So if you have, let's see here. Such a throwback to hear the pencil sharpener. It's really fun. Remember going there?
Sometimes breaking in it sometimes.
Yeah,
Yeah.
just hanging out. Okay, let's see here. So here's the previous answer button. And so this gives you the previous answer, which is handy, right? Often I can kind of make do with just reusing the previous answer, but let me see if I can remember how to store something. Let's say I want to store 14. Let me just try it. Store in. Okay. So to store values to be used later, let's say, for example, store 14, then what you're going to do is you're going to put, of course, 14 on your screen. So whatever you want to store on the screen. What you want to store on the screen. So if you found a value, then it's already on the screen. So that's good. And then what you're going to do is you're going to hit store, which is above the 7. And then it's going to not really prompt you anything, except it's super tiny, I think. 14, if I want to store it, then it shows up with like a little kind of, where do you want to put this thing? And it's super little over here. And your options are A, B, C, D, E, F. And that's all you have, I think. And so, and when you overwrite them, it just forgets about the previous ones. Okay, so if I want to store it in A, right, then
In my calculator, I have an answer, and then I have to hit alpha, and then there's also a previous answer. I got both on mine.
cool.
I don't know. Anyways.
So yeah, so the previous answer, but this is if you want to store something for like way later.
Okay.
Then usually what I do is I make a little note in my math and I say, oh, this is stored in A, right? And then I can go back and figure out where I stored things because it's not always obvious. Okay. And so now that 14 in this case, which is really simple, is stored in A. Now, if you want to recall it, then you have to, so now to recall what is stored in A, you have to go shift, of course. Shift and then copy. Recall, which is, oh,
Our calculator is a little different.
oh,
Ours, if so,
Can I
above
see
your
one?
AC button, there's M plus. That means you're adding something to the independent memory of the calculator. So if I do like 66 pi, then I hit M plus. It's gonna add it to memory, and then to recall it, you hit recall M plus. and
I
it'll
need to
bring
get
up
this
your
new
bits.
snazzy calculator.
You can store in ABC as well using shift store and then the alpha buttons A, B, C, D, E, and then.
Is there a store button? Yeah.
it's a
Okay.
store though.
Okay, okay. Yeah, they generally work the same way, but I should have this new snazzy one. Sounds like I'm shopping. Okay, let's see here. So shift recall. On mine, it gives me a list of all the values that are stored in what slots when I go shift recall. And so here, then it gives me, gives a list of values in memory. And I think I just have to hit, well, let's see here. I can't seem to scroll through, so that's okay. Shift A, no, Alpha A. So for me, to retrieve what is stored in A, I go Alpha A. I'll have to figure out how to do it. But usually it's something similar. Just know that you can store values, and once you figure that out, it's going to make things a lot easier, I think, especially for keeping all your decimal places, which is important in things like chemistry, water engineering, presumably. Okay, so it's just good to know how to use your calculator to the max, but I'm noticing that I have the M plus button that I've never cared about before. I need to read my manual. There, M plus, huh, cool. And then I guess that's M, whatever I grab from there. Okay, what was I doing? Aha! I had stored this big nasty thing in A, but I hadn't actually, so let's go back and do that. It was pi over 2 minus pi plus 2 in brackets. Now I'm going to store that in A. Do what I said I was going to do. And now I have that times 2, and then negative 40 divided by that is 5.600991535. Let's confirm that these are the same, or with some rounding problems. Negative 40 divided by negative pi -4, really hoping. Phew. $5.60099155 feels good. Why is that? Because I kept all the decimal places, right, in my calculator, so they should be the same, right? If I had used the rounded value here, then this would be slightly different because of rounding. Okay. Okay. What is, so if we let H be 5.6, you know what? I'm going to store this in B. How about that? Make a note to myself. Stored it in B. Because what do I want to do? Now, if that's the value of X, right, where it's maximized, then I can put that into as my R. So here, H is actually R in our case, right? X is R, H is the X value. Wow, that's confusing. So here, this happens at R equal to 5.6. I'll do approximately. So now I want to find what's this thing, right? So -3.571 R squared plus 40 R at R equal to 5.6, because that's going to maximize my area. So let's see here. I'm going to grab this jumble, copy. Whoa. Move these. So the area of R is this, or some version of that. And we're let R be 5 point, really rounded, but it's followed by 2, 0, I guess 0, 1. Let's do that. So now A of 5.601 is 5.601 squared times pi over 2 minus pi plus 2. But we have that thing saved in our calculator, right? So that's in store A, I think. Plus 40 times 5.601. But this is also stored in B. So then the output, okay, is store B squared times, for me, alpha A plus bracket 40 times alpha B. And I am not 100% confident that I didn't do it wrong. 112.019830.7. Let's see if we can confirm this with Desmos, just to check to see if I did it right or if I mucked something up along the way here.
We not do that with that K formula as well?
Yes. And did you get the same value? Yeah, then you're all good. I just don't have the K formula memorized. C plus B squared
C
over
minus B squared
C minus B squared.
over 4A.
See, I don't have it memorized. Probably. Well, they're all stored. You don't have to do this. How do I graph this in Desmos to check my work? Yeah, just don't. All right, well, nothing to see here. Just remember that the R's are being replaced by X's in Desmos, and that's it. That's it, she says. All right. I should have written it down. If I split the screen, I can't remember in this room, can you see it or no? It did not want to do that at all. Okay, but I do have both of them open. You just can't see it. I'm going to copy it in because otherwise it's really hard to see. I'm going to copy it in exactly like I have it. X squared times pi divided by 2. Step it up minus, oops, not a bracket yet. Minus bracket pi plus 2 end bracket plus 40x. Okay. Now it looks good. Keep this. Oops. There. Gonna crop this up. Just what we want. So here confirms that when x is 5.601, y is roughly 112.02, which is what we found, right? And so then the maximized area here is 112.02 when the radius of that half circle is 5.601. The area is maximized at 112.02. I don't know if we had any units, and I'm feet, square feet. When the radius of the half circle is 5.601 feet. Feels like quite a big window. Ooh. Well, it's maximized, I guess, with a perimeter of 40 feet. Right? That was our constraint. And what was the question? Don't want to go back there. What dimensions will maximize the area? Going back to answer the question here. You get it. This was 2 times R. 2 times 5.601 is roughly 11.202. This length was, okay, I will have to scroll up for that one. It was kind of a big one. It's just my iPad's making me so mad. using just the approximation of 5.601 because I'm lazy, I have 40 minus bracket 5.601 bracket times pi plus 2. Close the bracket, close that bracket. I'm going to wrap it all up in brackets. You can't see it anyways. Why is it just the same? Could I have simplified this all along? I don't see it. 20 minus r pi over 2 plus 1. I think I did something wrong. 5.601 times pi. Are you just getting back to r when you do it?
Yeah.
What did I miss? How can I simplify that to r? I guess I could. Can I? This one's just simplifying to r, so I'm going to leave it for a little bit and make sure that I didn't do. So I'm going to do this distance first, which is what? 2 pi r divided by 2, so pi r. Pi times 5.601. $17.596. Then what can I do? I can add the 17.596 plus 11.202. Oh, point would be nice. Oops. So then I get 40 minus 11.202 minus 17.596. It's, yeah, so it is R. I just don't see it. And then 11.202 divided by 2 because it's split evenly. It is R. It's a mystery to me. I'd have to spend more time working on it. We'll parking lot it. It is, it does work. I don't see it. 20 minus R over 2. Anyways. Satisfied? No, that's okay. Me neither. I'll have to come back to that. But it does work out and it is R. I just am not entirely convinced yet. There. So those are the dimensions of this window. Okay. Hit it. If we want to find, it's scrolling around in here. If we want to know the behavior of a quadratic then one of the main things that we do is, well, we know that it's going to be a parabola either facing up or facing down. And the next thing we can find are the intercepts. Of course, we can find the y-intercepts. And usually we're mostly interested in the horizontal intercepts where it goes through the x-axis. Because if I want to find the y-intercept, what do? I just plug in x equals 0 and then I solve it and that's fine. Or I evaluate it and then I get the values. But in terms of the horizontal intercepts, right, that's where it crosses the x-axis, which is where y is equal to 0, right? A couple of different options. Either it's above or potentially below the x-axis, and then it'll never cross if it's facing down, right? So then you have no horizontal intercepts. That can happen. If you have it just bouncing off the x-axis, then there's one horizontal intercept, and then it can be crossing at 2 horizontal intercepts. And so our goal is to find those horizontal intercepts. Now we can do the same thing where we do all the math to derive the quadratic formula, but I think we're mature enough and probably tired enough to just go for it. Okay? And so to find the horizontal intercepts of a quadratic, we can use the quadratic formula. If the quadratic is in standard form, if the quadratic is in standard form, which is ax squared plus bx plus c. I'm going to give it to you. It's on your formula sheet, and it says that x is going to be negative b plus minus the square root of b squared minus 4ac over 2a. Not too bad. We have a plus and a minus because you're potentially looking for 2 points, right? And so you've got your negative b, and then you go up the square root of b squared minus 4ac, right? And then divide that by 2a, and then you go down a little bit from negative b. And so that's how we get these potentially two intercepts. I think there is an example, but before we do, I just want you to remember that we can't take the square root of a negative number, right? That's a fact. And so we can't take the square root of a negative number, right? It's not in the domain, which we've worked on already. And so what does that mean? If you find a negative value in the square root, that's just telling you that there are no horizontal intercepts. Okay. So if you find b squared minus 4ac is less than 0, right? That means there are no solutions, which is really saying no horizontal intercepts. I bring that up because that can totally happen if you have something like this, right? No horizontal intercepts, and even like this, there's no horizontal intercepts. Right, so it is something that's going to happen, and you just need to recognize it, right? If you find that this is negative, then you're off the hook. You're done. No horizontal intercepts. All right. I'm sure he's got an example for us. Let's wait. Oh my gosh. It's killing me. I'm a pretty patient person, I think, except when I'm waiting on technology. I can't handle it. Okay, so the vertical intercept, right? We said that one's pretty breezy. The vertical intercept is when x is equal to 0. The horizontal intercept is the sneakier one. That's when f of x is equal to 0, right? When your y is equal to 0. And that's when we have a quadratic, that's when we use the quadratic formula. So what I want to do is just find the vertical intercept. That's a good place to start. And so f of 0 is 2 times 0 squared plus 5 times 0 minus 3. So the vertical intercept is when y is -3. And so on a graph, might look something like this. And so when x is 0, you're at -3. It's facing up, right? Because 2 is positive, so the coefficient on x squared is positive, and so it's facing up. So I already know I'm going to have solutions. In fact, I should have 2 solutions. Why? Because it's going to look something like this, right? So I'm expecting to have 2 horizontal intercepts. So what I'm going to do here is I want f of x, I'll put it on a fresh page here, 2x squared plus 5x minus 3. I'm going to force it to be 0. 0 is 2x squared plus 5x minus 3. Now I can use the quadratic formula and say that a is 2, b is 5, and c is -3. Don't forget that negative like I did. I saved it, but still close. It doesn't look like 3. Okay. So now x is -b plus minus the square root of b squared minus 4ac divided by 2a. Plug and chug. This is going to be -5 plus minus the square root of 5 squared minus 4 times 2 times -3. All divided by 2 times 2. Oh. Five squared is 25. And then I have minus bracket 4 times 2 times -3. Whoops. I get the square root of 49, which is not negative, so that's good. So if I take the square root of 49, I get a nice 7, which means that I'm going to have -5. I like to do the minus first because it's going to be the smaller version, right? And then you have them from smaller to largest. But if you, it doesn't really matter in this case. So -5 minus, and I'll do 7. divided by 4, comma, -5 plus 7, keep wanting to do the square root, divided by 4. So if I do -5 minus 7, puts me at -12 divided by 4.
Wait,
Yes.
I'm confused how you got root 49.
Oh, did I do it wrong?
Well, isn't it like 5 squared just minus that number, or is it?
There's two negatives up there on the right side, so it'll be a positive number.
Yeah, so here this negative makes it positive. So if you do
Okay.
4 times 2 times -3, I get -24.
Yeah, okay.
But then
And so
minus,
that takes away that negative there.
yeah, so I get minus, so it looks like this. 25 minus -24.
Okay. Thanks.
And that gets me to root 49. Nice. Good. Little sneaky. -5 plus 7 is 2 divided by 4, which is usually 1/2, but I'll confirm. I'll do 0.5. So what that means is we have horizontal intercepts at -3 is 0, right? We force the output to be 0, so we know that's true. But how can you check your work? You could put in -3 into the equation, right? This original equation, and just confirm that it equals 0. That's a good way to check it, right? And then you can plug in 0.5 and you can confirm that it equals 0. And then that's the definition of the horizontal intercept. So, and 0.50. We can also use Desmos. I can remember I think I've got it here. 2x squared plus 5x minus 3. Was that us? I've got my, pop them up here. Oh, not yet. Delete. I wanted that one too. So we can always confirm it with Desmos if we have it, right? Especially if you're working on an assignment, then you can check your work, and that's always a good idea. But the quadratic formula is going to save you some time trying to find those intercepts, right? Especially if you have a quadratic in standard form. And then we know how to find the vertex, right? H is -b over 2a, right? And then that's how we find this -1.25. Look at us go. We've got all these key players down pat. Okay. I wanted to do another example, but my iPad is driving me nuts. There. Whoa. Yeah. Okay. It's because I got sassy with it. Doesn't like that. I wanted to do, okay, fine. Okay, fine. So we're gonna find the horizontal and the vertical intercepts again. Right now, I have a negative coefficient on my leading term, right? And so now I know it's gonna be facing down. And so I could have horizontal intercepts, but if it's below the x-axis, then I don't, right? And so let's go ahead and find the vertical intercept first. G of 0, that's kind of a gimme one. 2 times 0 plus 5. So the vertical intercept is at 0, 5. So if I have to visualize this thing, I'm up here at 5, and it might go something like this because it's facing down. So again, I'm expecting 2 horizontal intercepts. All right. If I want g of x equal to negative x squared minus 2x plus 5, force it to be 0. That's how I'm going to find my horizontal intercepts. Quadratic formula again, x is negative b plus minus the square root of b squared minus 4ac divided by 2a. Kind of picking up the pace a little bit. Negative 2 is 2 plus minus negative 2 squared is 4 minus 4 times, and you know what, I shouldn't write it like that. Negative 2 squared, but in my head I'm saying 4 minus 4 times a, which is negative 1, times c, which is 5. Divided by, I always forget the 2a, 2 times negative 1. Two plus minus 4 minus negative 20 puts me at the root of 24, which is not a nice number. Oops, negative 2. Your calculator will turn the root of 24 into 2 times the root of 6, right? If it simplifies it, which is nice. Then you could cancel 2's all around, but you'd still have to do the same amount of math. And so I'm opting not to, but that's up to you. 2 minus root 24 divided by negative 2. And 2 plus root 24 divided by negative 2. 2 minus the root of 24 divided by negative 2. Negative 1 plus root 6. I didn't do that in my head. The calculator just does it. It should be giving you exact answers. And 2 plus root 24 divided by negative 2 is negative 1 minus root 6, right? Because all those 2's cancel. Because root 24 you can rewrite as 2 root 6. I didn't, but I'm letting the calculator do it, which I can approximate. I should have done the previous one too. Negative 3.449 for a 9743. I can't stop.
Which mode does your calculator have to be to give the roots? Mine's just given the decimal.
Yeah, me too.
Really? Oh boy. That's okay. I think I'll have to Google how to change it to default to exact answers. It's nice to get the decimals. In terms of what I'm expecting, if you just land on the approximation, that's totally fine. I'm fine with that. right? I'm only writing these out because my calculator gives it to me. And I'm sure, yeah, you change probably the defaults and then it'll do it.
Well, it's weird. It's like sometimes depending on the number, when you hit the SD, it'll
Yeah.
give you different stuff, but right on this one specifically, it's just giving the decimal.
Doesn't like the root, huh? What if you do the root of 24? What does it do?
Decimal.
Decimal.
Decimal only.
Huh. That's weird.
It says 2 root 6. Oh, you know. Got a D on the top. I think you D in the math. D math up arrow.
Why do you get the up arrow?
Sounds like we're just a Google away. Horizontal intercepts at negative 3.450 and 1.45, let's say, 0. And with that, I release you. If you have any questions, let me know. But yeah, might be worth a Google to see how you get those exact answers as your defaults. We'll stop this recording.
How'd it go?